All right, kids, section 8.5. We have one more to go after this, 8.6, before we get to the mid-unit break. But 8.5 is talking about the area between curves with respect to y this time. So some things change. Here's the deal now. You have a representative rectangle that is now horizontal instead of vertical. That's the difference. I kind of mentioned that in the last video. But here's what it looks like now, my representative rectangle. But there are some things that you have to do a little differently this time. This time it's going to be, see how your rectangle, the right-hand side hits the line, the left-hand side hits the square root of x. These are right minus left instead of top minus bottom. All right, so that's the first thing that makes these different when you're going horizontal. Second thing is, the function has to be solved for x. See how most times we have it y equals? This time you need to take the functions, must be solved for x. Functions must, in other words, they have to be x equals. So you got to switch them. So that's the second thing that's most important with these. And the third thing is that your bounds are y values, not x values. So those are the three big factors that come into play when you are looking at area between curves with respect to y. So I'm going to bubble this in. This is really super duper important. There you go. So set up the integral that allows you to find the area in the first quadrant that's bounded by the square root of x and below the line x minus 6. So they shaded it for you and made it all pretty. Well, this is really pretty easy. What I need to know though are what are the y values. This one right here, at the lowest value it hits is 0. The highest value it hits up here is 3, right? A y value of 3. So my bounds are 0 to 3. Good so far. But I've got an issue with this, because when I go to put these into my integral, the function has to be solved for x. So if y equals the square root of x, I have to square both sides. X would equal y squared. And if I take this line and solve it for x, it's going to be x equals y plus 6. And so that's what I have to use in my integral. So my integral is the right, oh, I already had an integral. The right-hand side, the right is the line, y plus 6. The left side of my rectangle hits the square root of x, which is y squared. And this time it's with respect to y because I've got all y values as my bounds and I've got y's in my equation. And there you go. I guess I could clean it up a little bit. If I were to clean it up a little bit, it would go 0 to 3 of y plus 6 minus y squared dy. Now, could I have done this with respect to x? And the answer is yeah. The problem with respect to x, though, is that I'd have to split it right here because see what's on top would be the function, the bottom is the x-axis, but over here what's on top is the function, the square root of x, and the bottom is the line. So I'd have to switch it into two separate pieces. And if I were savvy and did that, here would be what it would look like, and it's going to get you the same answer. It's the same as, if I were to look at it x-wise, it would be 0 to 6 of the square root of x with respect to x plus 6 to 9. I'd have to split that, remember, 6 to 9 of the square root of x minus the line x minus 6 dx. So they would give you the same answer. It's just, it's sometimes easier to go one way versus the other. Obviously this, looking at it from the y perspective, made this a little bit simpler as the integral. I wouldn't have to do two separate ones. But just an FYI, you're going to get the same answer either way. Here comes number 2. Number 2 says, set up the integral, don't solve it, to find the area. And they give you, here's your x equals 3 minus y squared. That's this guy. He's like a sideways parabola. And x equals y plus 1. That's the line. So I draw my representative rectangle because they want me to do this with being in terms of y's. I've got to figure out my y coordinates. And so I look here. Here's where one intersection is. that's at -2. The other intersections up here, that's at +1. I'm looking at what the y values are. And so I set up my integral. Here I go. It's going from -2 to 1. Right minus left. Parabola. They already have it solved for me. That's nice of them. They don't normally do that. Sideways parabola, 3 minus y squared, minus the left, which is the line, y plus 1. I would use parentheses because otherwise you're not going to remember to distribute that negative. I can clean it up just slightly. -2 to 1. I have a negative y squared. I have a negative y. And I have a 3 minus 1, so I get 2 plus 2. There it is. That's the best I got. Okay, so the third one, they want us to do this thing, and they want us to do it both ways, with respect to x and with respect to y. So there's some coordinates that I need to know in order to be able to do that. So let's see if we can kind of figure that out first. I need to know this guy here is 0, 1. This guy here, I want to know where the line, which one's my line? This guy, 3/2 x plus 1 equals my upside down parabola 2 minus x squared. So I'm going to have to graph these and figure out that point of intersection, but I'll tell you that it comes out to be 0.5 comma 1.75. That's this coordinate. This coordinate here is another important one to us, and that is the coordinate 1.366 and 1.34. I think that's it for values. All right, so with respect to x, that means I'm going with vertical representative rectangles. This thing is so dark I don't know that you could even see if I were to draw on here. But if I were to look at a representative rectangle over here, the top is the line, the bottom is the parabola. That's great. But it changes at this coordinate right here. And at this coordinate right here, it changes to the parabola being on top and the unhappy parabola being on top and the happy parabola being on the bottom. So if I were to do this with respect to x, the first one goes x is 0 to 0.5. 0.5. Top minus bottom. Top is the line. 3/2 x plus 1. Bottom is the happy parabola, which is x minus 1 quantity squared. Oh, wait a minute, let me look. 0 to 0.5, line, and happy parabola. All right, that's with respect to x. Second one goes plus. Now I have my representative rectangle here, unhappy parabola over happy parabola. So this one's now going from 0.5 to 1.366. 0.5 to 1.366. And that would be, again, top minus bottom, unhappy parabola, 2 minus x squared, minus happy parabola, x minus 1 quantity squared. Now for some reason, let me go back and look at this first part here. For some reason, when I copied from the lesson video, it said that this was 2 minus, this was the unhappy parabola. I don't think I agree with that, so I'm not sure if it was my mistake in writing it down or if it was their mistake in the video, but nonetheless, the top of this rectangle definitely is hitting the line, and the bottom of this rectangle is definitely hitting the happy parabola. So I'm going to keep it on what I've got going on there. But they did have that switch, so just an FYI. Alright, so that would be that one. But how about if I went the other way, if I went with respect to y with horizontal rectangles going on? This one would be, I've got a few different things going on. This one would have to be divided into 3 sections, and I'm not so sure that you can see it, but the first one would be this. I divide it this way, right minus left. Right is the unhappy parabola, left is the line. But then I also have another split down here, because in between here, right is the line and left is the happy parabola. Down here I've got the just the parabola on both sides, right? That's hitting the parabola both ways. And so if I'm looking at this guy, and this goes, I'm looking at my y values, right, because I'm going horizontal with this. So I need to know what these y coordinates are. The first one goes from 0 to 1.34. The next one goes from 1.34 to 1. And the last one goes from 1 to 1.75. So now I'm looking at it horizontally in 3 sections. So this one's going to be a little bit trickier. Let's see if we can set it up. The other thing too is my functions need to be solved for x, and they're not. So the first job I have is to solve these for x. So if I have y equals 2 minus x squared, then I have x squared equals 2 minus y. If I solve for x, that means I'm square rooting the other thing. X equals the square root of 2 minus y. If I take the next guy and say y equals x minus 1 squared, then this would be the square root of y equals x minus 1, or the square root of y is plus 1 equals x. And the last one, if I take this guy and solve for x, it's going to be, I'm going to multiply by 2. 2y equals 3x plus 2. Solve for solve for x. Sorry, I'm so used to solving for y. All right, 2y minus 2, x equals 2y minus 2 over 3. So now I have all the pieces, and now I need to put my integrals together. First integral goes from 0 to a y value of 1.34. 0, 1.34. Right minus left. Right is the square root of y plus 1, right? The right is this part, square root of y plus 1, minus the left, which funny enough is also the square root of y plus 1, right? That's this side. Right and left are the same. dy plus. Next section is this section. My y values go from 1.34. How can that be? Oh, 0.134. That's what I'm looking at. This should be a 0.134. I'm like, that can't happen. 0.134. Let me fix that. 0.134. Okay, so from 0.134 to 1. That's this section in here. The right is the unhappy parabola, this guy, square root of 2 minus y, minus the left, which is the happy parabola. Happy parabola is this guy. It is the square root of y plus 1. Last guy goes from 1 to 1.75. And that one is right minus left. Unhappy parabola, square root of 2 minus y, minus your happy, the left-hand side, which is the line. The line's this guy. 2y minus 2 all over 3. Now, thank God they didn't ask me to evaluate that, but that's what it is. That's what your answer is. So it'd have to be in 3 different parts. So in this case, doing it around the x-axis with respect to x is the way to go. One shot deal, short and sweet, where this has to be divided into 3 sections. Okay, that does the examples. Let me do a couple of practice problems with you. First one I chose was number 3. Number 3, directions say, set up the integral with respect to y that represents the area. Don't solve. Okay, so number 3, first thing I have to do is have them in terms of x. So x would equal 3 minus y. In this case, x would equal y plus 2. Let's figure out which one's which. Well, the negative x plus 3 has the negative slope. That's this one. So this guy is the 3 minus y. X equals. This one has a positive slope. Positive slope guy. He's an x equals y plus 2. And so again, if I'm going horizontal on this, I'm looking at representative rectangles. So like it would be here. Just an arbitrary rectangle right about there. But if I look at it over here, the right and the left change. In this case, the right is 3 minus y, the left is 0. In this case, the right is y plus 2, the left is 0. So it changes. Where does it change? It changes right here, wherever that is. So I need to figure out where that is, because that's where the change happens, and that's how I'm going to split my integrals. So if I look at the change, I'm setting 3 minus y equal to y plus 2, and I'm going to see what that comes out to be. 2y equals 1, and y is 1/2. Makes sense, 1/2. That looks like about where it is. All right, so that's my split. I've got 0 to 1/2 of, let's see, 0 to 1/2. That's this bottom. Oh, actually, no, it's -3, right? It starts at -3 down here. -3 to 1/2. That would be better. And that one has the right being 3 minus y and the left being 0. Actually, no, the left is at -1, isn't it? Here's where the axis is, and it's over at -1. So -1. Ooh, fancy pants there. Plus, the next one goes from 1/2 to 3. No, 4 to 4. And this time the right is the line. Ooh, did I get those backwards? I think I did. This one, the right, was the line y plus 2. Did you catch that? This guy right is y plus 2. This guy, the right, is 3 minus y. The left is -1. All right, there we go. And then just a matter of cleaning it up. So if I make it any prettier, I'm going to say, and I might go into this box over here. So it's the integral from -3 to 1/2 of y plus 2 plus 1 plus 3. This one's going to be the integral from 1/2 to 4, and it is 3 minus y plus 1 more is 4 minus y. There you go. 4 minus y dy. They said set it up. They said don't solve it, and you say okay. All right, here comes the next one. Number 6. Number 6 says sketch the graphs here. Do this with respect to x. Do it with respect to y. See what you think. I have a squared graph, a parabola. Happy parabola. I have a y equals 5. I'm going to make this my 5. Y equals 5. This was y equals x squared. I have an x equals -2 and an x equals 1. Okay. So I have some places where I need to know where the area that I'm talking about is the area bounded by all these things. So from here over, down here, there it is. Nice and pretty. All right, now the easiest one is when you're doing it with respect to x, because that's going to be a representative rectangle like this, right? Vertical, because it's the x equals, I have bounds that are x bounds. So my x's go on the left between -2, on the right to 1, top minus bottom, right? This is back top minus bottom, top is 5, minus the bottom, which is x squared. Done. That's it. So you're like, sweet, that is a nice thing. But it gets quite a bit more complicated when I go the other way. Because when I go horizontal with this, because I need to split it into 3 different pieces. Piece number 1, I don't know if this color is going to come out very well. Piece number 1 horizontally would be like this, right here. It would be 0 to that point right here. Piece number 2 is this piece that goes to here. And then piece number 3 is this rectangle type thing that goes to 5. So the question is, where are these things? So let's think of this coordinate. If x is 1, y would be 1 also, because I'm just putting it into y equals x squared for now. So this would be a 1, 1. All right, then I go to the next one. If x is -2, what's this coordinate? -2, 4, right? -2 squared would be 4. That's my next piece. And then my last piece goes from 4 to 5. Now my graph is kind of out of kilter on this a bit, but you get the idea. So got those coordinates. That's really important to us. And then the second thing is I've got to look at is, remember, we've got to change these equations so they're solved for x. So if I want to find x, x is, take the square root, the square root of y, plus or minus the square root of y. I don't need anybody else. There are no other formulas. All right, so let's see if we can split this up and figure this out. First situation is in here, right? That would be my representative rectangle. So if I'm in that space, I am going from 0 to 1, my y value, and I am right minus left. The right side of this thing hits the square root of y. This is the square root, positive square root. This is the negative square root of y, so minus the negative square root of y. There's my first box. Second one goes from 1 to 4, right? Y values. So 1 to 4. And in this case, my representative rectangle looks this way. It's going to be the right-hand side hits 1, hits this 1 block. So the right-hand side is 1 minus, and then the left-hand side hits that negative square root of y. And then the third one's simple. The third one goes the integral from 4 to 5. And that's just 5. The top hits, actually, let me go this way. The right, I'm going right and left. The right hits 1. The left hits a -2. That's this box. 1, -2. So let's see if we can clean it up and put it together. I'm going to go come down into box number 8. I have 3 parts to this. First part goes 0 to 1 of the square root of y plus another square root of y is 2 square roots of y, dy. Plus. Next one goes from 1 to 4. This would be 1 plus the square root of y, dy. Last one goes from 4 to 5. 1 plus 2 is 3, and there's your final answer for going in the y direction. Certainly going in the x direction would have been a lot easier for this one. So sometimes you have choices to make. They don't tell you which way you have to go, but in this case that would have been nice. So last one, number 9. This is it. I want to tell you that you can do this with a calculator. It gets really messy without it, so we're just going to go with. Let R be the region graphed by the square root of x. That's this guy, y equals the square root of x. And then the uppy guy is your sine, this crazy sine function. Y equals 4 over pi sine to the -1 of x over 4. Okay. What's the area of the region? Hint, integrating with respect to y is easier than integrating with respect to x. So let's think about our representative rectangle. If I integrate with respect to y, I'm going horizontal representative rectangle. And it's consistent. The right always hits the sine graph thing, and the left always hits the square root of x. So yes, that's cool. So I'm going to set this up. I need to know what these points are. This guy's at 0, 0, of course. This guy here, I don't know where he is, but I'm going to go and figure that out. it actually is, let's see, I can see from the graph, it's the 0.42. So if I set up the integral is going with the y value, 0 to 2. But then I have to take these guys, and I can't use them solved for y equals. It has to be an x equals situation. So that's my next task. So I know that this guy here, I know I have, let me come down here. Y equals the square root of x means that x equals y squared. Right, that's my first one. The second one's the one that gets nasty. Y equals 4 over pi sine to the negative 1 of x over 4. And you're like, how on earth am I supposed to solve that for x? You kind of know how, but I think you'd get stuck on this, which is why I chose it. I'm going to multiply both sides by 4 over pi, so I'm going to divide by 4 over pi, so it's going to give me a pi over 4 y equals sine to the negative 1 of x over 4. Well, if I try to solve this, I need to use inverse sine rules. In other words, this is telling me that when I value this, it's going to be the sine of 4 pi over y, 4 pi over y. I'm inversing these things. So 4 pi over y equals x over 4. That's how that inverse works. You flip-flop them. Which means that if I take this and solve for x, x is going to equal 4 times the sine of 4 pi over y. All right, now the hard work's done because the rest of this is pretty simple. The right minus left. Right is this crazy formula that we just figured out. So 4 sine of 4 pi over y. That's my right, minus my left of the square root of x, which we said was y squared. So I go to the handy dandy calculator and I calculate out what that is. Now, when you put this in the calculator, you can put it in as x's and it'll give you the same answer. Obviously, for the problem, you've got to have it in terms of y, but when you go to calculate it in the calculator, if you keep the variable the same, it's going to give you the same answer. Answer is 2.426. All right, that takes care of section 8.5. One to go before we get to the mid-unit. I will see you in class. Let me know if you have any questions.